it clogged up here, but it stayed clean down here, so that shows that we're not building up cakes on our bags that are slowing things down. We should be fine for our 5 micron high speed. That's where we're going in steps down at filter size. If we went straight to 5 micron, we would clog those things up in a New York minute. And also, we don't want to clean it up so fast that we don't get a good correlation on our turbidity. You rinse the top too.
Yeah, my name is Robbie Domang. I'm the interface lead on the water injection project for Phase 1. Roles are pretty vast, working closely with the topsides and subsea teams on the interfaces between the groups, and activities involved with getting the water down to the cleanliness levels we're expecting.
I think it's a very interesting test. It's very important that we get the amount of cleanliness that we're trying to reach. 5 microns is a very hard task to reach, but they've done a good job of trying to reach that. The turbidity test that they're doing seems pretty ingenious in how they're trying to figure out the correlation between turbidity and water cleanliness. So if they can achieve that and effect that offshore, it's going to make operations go a lot smoother.
Kind of what I'm interested in here today is to look at the velocities that were coming out of this testing, to know more about how subsea is going to complete their commissioning, because it feeds into the work we're doing on topsides.
The problem with subsea is it's very hard to get samples of anything to bring back, and it takes time to do that. So with a turbidity meter, we're able to measure, if you will, on the fly as we're doing the work, and give us a good indication when we think we can stop the work, the flushing, and actually take the sample so we can be more efficient, because we're in very deep water, a long way from shore, with very expensive boats that takes at least 4 hours to go down and come back with anything subsea from the top where the boat's located above the water. So this is a very efficient process. The other reason we want to do this is everything we can test on shore, we need to do it on shore. It's the cheapest place, it's the best place to do any new technology. So that's this whole pigging loop here is all about making sure before we take it offshore that everything's vetted as much as we possibly can under the worst conditions, so when we do take it offshore, we have confidence that it's going to work.
So I think the guys did a fantastic job in trying to set this up and get it all arranged. The flushing is a dual process because it benefits not only the subsea portion but also the topsides. So we're kind of combining two efforts in one here today. Based on what I've seen so far, I think the initial results look pretty promising. Only from the standpoint that the turbidity issues around here, which is the color of the cloudiness of the water, we are trying to see if the turbidity meter can correlate the dirtiness and the frequency of the flushing to the end result, which is the solids that we're trying to get, which is below 2 milligrams per liter of solids and 5 parts per million in the actual water. So the initial results look pretty promising here.
The testing's going really well. The expectations were, there were no expectations, but we made sure to clean up the water really slowly so we get a good correlation from water cleanliness to turbidity through the turbidity meter. And the real choice section is coming up next when we start running at high speed and seeing if stuff actually gets pulled off the walls of the pipe and pushed through the filters. So we're going to be analyzing that with the flow rate and the turbidity meter and all that. So that's what we want to see. You know, all this is pretty much like worst case offshore. We're going to take this dirty 10 micron filter out of the inlet filter pot. We're going to move it to the outlet filter pot, keep the water clean as it returns to the tanks. We're going to put fresh 5 micron filters in the inlet pot. That's the final stage of our low flow flushing.
From here we take the samples into the lab, and in the lab we have technicians that are going to run TSS, total suspended solids analysis on them, and then later they will run particle size analysis on them. Again, this data is for our verification of cleanliness passing through our filters and when we're trying to clean subsea. So from here they go directly inside. We'll select 3 or 4 samples. They'll run a TSS analysis and particle size analysis.
We're taking 5 samples because as the turbidity gets lower, they need more and more fluid to get an accurate reading in the lab.
Schmidt, Thunder Horsewater Injection Commissioning Lead. Today we're out here at Baker facility working on phase 1 test 2 of our procedure. Today what we'll be doing is increasing our flow rate from 225 GPM all the way up to 2500 GPM. What we're expecting to see today is every time we increase the flow rate, we should see a spike in turbidity readings. We pick up more entrained particles and carry them out the other side of the loop. Our threshold, or where we think we'll see a lot of action, will be 1000 GPM, in which case at that point in time all of the 100 micron particles should be lifted from the downside of the loop and carried up over and out of the flow loop. So we expect to see an increase in turbidity, and then it should always average out to our target of around 0.25 or 0.5 FTU. We stopped our pumps at 1300 GPM. We're going to swap out our 5 micron filters. But if you can see behind us, this is the sort of downstream side of the loop. And what we're looking for today is around 1100 GPM or 1000 GPM. We expected all the particles stuck on this side of the loop to be lifted and carried up over the riser, in which case then we were going to see the turbidity reading spike, which is exactly what we saw when we increased our flow rate to 1100 GPM. Our turbidity readings spiked up, and it took a long time for them to average out as we were picking up particles from the downstream portion of the loop and carrying them up over the risers. 25.
adjusting the depth so that it gets the proper reading. Debris at the bottom of this that shows that at slow flow rates we weren't able to carry over the large heavy particles over the riser sections of this loop, but once we increased the max flow rate we were obviously able to pick it up and carry it out of there, and that's what these bags were for, to catch it, so we were sure that it was carrying it out of there.